The first model, used where the ventilators are more than 2 meters from the edge of the reservoir, is shown here. As you can see, the depth of smoke, D, is raised to the power 2, and this reflects the fact that the maximum allowable exhaust rate, M crit, increases rapidly with increasing layer depth. Most of the variables in the equation you'll recognise, but there is the variable WV in the equation that you have not seen before, and this is the diameter of the ventilator. But it's not quite as simple as being the diameter because of the way that the formula has been constructed. WV is in fact the diameter of a circle that has the same area as the ventilator. This is the simplest way that the developers of the formula could cater for all the various sizes and shapes of ventilators that are available. The output from the model is expressed as M crit and is given in kilograms per second. This is the upper limit for the amount of smoke that can pass through a given ventilator without plug holing occurring. If we have an M crit value of 50 kilograms per second, and we also calculate that in the worst case we have 30 kilograms per second flowing out of any one single ventilator, then our flow is below the upper limit and we can be sure that plug holing will not occur. If, however, the actual flow out of the ventilator is shown to be 70 kilograms per second, compared to our M crit value of 50 kilograms per second, then the 70 kilograms is over the upper limit and we can be confident that plug holing is likely to occur. And in this cases, we would probably need more ventilators, probably of a smaller size. Using our last example, where the mass flow rate was calculated at 46.7 kilograms per second, we calculated theta as being 85 Kelvin and TL as being 373 Kelvin. And the required aerodynamic free area of ventilation per reservoir was 12.6 square meters. Let's suppose that the designer has checked that the 20 meter and 10 meter rule for stagnation has been adhered to, and that ventilators with a geometric area of 4 square meters have been selected. The geometric area equates to an aerodynamic free area of 2.4 square meters for each ventilator, and we shall need 12.6 divided by 2.4, which equals 6 when rounded up, of these ventilators to ensure that we have sufficient aggregate ventilation area in the reservoir. The geometric area of 4 square meters is the one that we have to convert to give us a value of WV to put into the formula for M crit. WV is calculated as shown here. In our example, WV comes out at 2.26 meters. So this is a figure we have to put into the formula for M crit. Our formula for M crit then becomes M crit equals 2.05 times 1.2 times, in the brackets, 9.81 times 288 times 85, all raised to the power of half, multiplied by 3 squared, multiplied by 2.26 raised to the power of half, and all divided by 373. This comes out at 43.68 kilograms per second. So we know from this that if we have more than 43.68 kilograms per second leaving any ventilator, then plug holing is likely to occur. In our example, the total flow rate for all smoke is 46.7 kilograms per second. And remember that this smoke is flowing out of all 6 of the ventilators that are provided in the reservoir. So we also know that the most smoke that will flow out of any one ventilator is 46.7 divided by 6, which equals 7.8 kilograms per second. This actual amount that is flowing out of each ventilator is much lower than the M crit limit, and so we can be confident that plug holing will not occur in this case.